What's up, guys? Today we're going to learn how to write our first set theory proof using a technique called direct proof. Let's check it out. So the problem starts by defining a few sets, A, B, and C. And the conditional statement that we're asked to prove is that if A is a subset of B, then the intersection of A and C is a subset of the intersection of B and C. And in symbols, we typically express implications as P implies Q, where P is the proposition that follows if. This is called the hypothesis. And Q is the proposition that follows then. This is called the conclusion. Okay, now before we even write the proof, I want to sort of just draw out this situation and try to make it a little less abstract and a bit more intuitive. So what I'm going to do is I'm going to draw two sets such that A is a subset of B. And now I'm going to draw a set C such that C intersects both A and B here. And as we can see, A being a subset of B does in fact lead to the intersection of A and C that I just shaded here being a subset of the intersection of B and C. Okay, and so visually this makes sense. And now it's our job to sort of put this in words and go ahead and write the proof. So today we're using a technique called direct proof. And how direct proof works is you suppose that P is true. You suppose that the hypothesis is true. And then you prove that Q follows as a result. And so that's the first step here, is to suppose that P is true here. Okay, so we're going to go ahead and suppose that A is a subset of B. Now, again, what's the goal? The goal is to prove that the intersection of A and C is a subset of the intersection of B and C. And what does that mean? So here we need to be really comfortable with our set theory definitions. The intersection of A and C is a subset of the intersection of B and C if and only if an element that we'll call X belonging to the intersection of A and C implies that the element also belongs to the intersection of B and C. And now what this does is it uncovers another conditional statement, another implication that we can prove directly. And again, how do we prove this directly? Well, we suppose the hypothesis. We suppose P. Okay, so I'm going to suppose that X, some element X, belongs to the intersection of A and C. Now we can unpack this a little bit. Okay, this gives us information. Okay, the definition of intersection tells us that X must belong to both A and C independently. Okay, so now we know that X has to belong to A and it has to also belong to C. Okay, so we suppose this to be true. And now, in order to prove this proposition here, right, the goal, we need to conclude that X belongs to the intersection of B and C. And again, by definition, X would belong to the intersection of B and C if and only if X belonged to B and it also belonged to C. So we need to sort of see if we have enough information to conclude this. Well, we already know that X belongs to C, so we're good there. Now we just need to see if X belongs to B as well. And it turns out we never really unpacked our initial supposition here. Okay, we suppose that A was a subset of B. Okay, now why is this important? Because by definition of subset, A is a subset of B if and only if an element belonging to A implies that the element also belongs to B. And we know that the element already belongs to A, and we know A is a subset of B, so it must be true that X belongs to B as well. The conclusion has to be true here. Okay? So now that we know that X belongs to B, and we already knew that X belonged to C, we now have enough information to conclude that X belongs to the intersection of B and C. Okay. So now that we've satisfied this conditional statement, we can therefore conclude that the intersection of A and C is in fact a subset of the intersection of B and C. And with that, we supposed that P was true, and we concluded that Q followed as a result, and therefore we've successfully proven the conditional statement. And with that said, it's been demonstrated.